Welcome to today's paper reading. Today's paper is titled, Mixture of Agents Enhances Large Language Model Capabilities. This paper, titled Mixture of Agents Enhances Large Language Model Capabilities, is authored by Junlin, Wang and colleagues from Duke University, Together AI, University of Chicago, and Stanford University. It is currently under review as a preprint. The abstract highlights recent advancements in large language models, LLMs, emphasizing their capabilities in natural language understanding and generation tasks. As the number of LLMs grows, the challenge of leveraging their collective expertise becomes increasingly important. To address this, the authors propose a novel approach called Mixture of Agents, MOA. This methodology involves a layered architecture where each layer consists of multiple LLM agents. Each agent in the MOA uses the outputs from agents in the previous layer as auxiliary information to generate its response. The MOA models have demonstrated state-of-the-art performance on benchmarks such as Alpaca-Eval 2.0, MTBench, and Flask, outperforming models like GPT-4 Omni. Notably, a MOA model using only open-source LLMs leads Alpaca-Eval 2.0 with a significant score of 65.1%, compared to GPT-4 Omni's 57.5%. The introduction of this paper highlights the inherent collaborativeness of large language models, LLMs. These models tend to generate better responses when they are provided with outputs from other models, even if those outputs are of lower quality. This phenomenon is evident in the significant improvement of LC win rates when LLMs are presented with collaborative responses. Based on this finding, the paper introduces the Mixture of Agents, MOA, methodology, which involves an iterative refinement process using multiple layers of LLMs to enhance response quality. The MOA framework has been evaluated comprehensively using benchmarks such as Alpaca-Eval 2.0, MTBench, and Flask, demonstrating substantial improvements and achieving a new state-of-the-art win rate of 65.8% on Alpaca-Eval 2.0. Figure 1 illustrates the improvement in LC win rates on the Alpaca-Eval 2.0 benchmark when LLMs are provided with responses generated by other models. This collaborative effect, termed the collaborativeness phenomenon, is observed across various LLMs. Notably, the win rates improve even when the auxiliary responses are of lower quality than what the individual LLMs could generate independently. Figure 2 illustrates the Mixture of Agents, MOA, structure, which consists of 4 layers, each containing 3 agents. These agents can utilize the same model for processing. The MOA methodology involves an iterative refinement process where responses generated by agents in one layer are further refined by agents in subsequent layers, aiming to enhance the overall quality of the output. The Mixture of Agents methodology leverages the collaborative nature of large language models, LLMs. These models can enhance their responses by referencing outputs from other models. This collaboration is characterized by 2 distinct roles: proposers, which generate diverse reference responses, and aggregators, which synthesize these responses into high-quality outputs. For instance, models like GPT-4o, Qwen 1.5, and Llama 3 show versatility in both roles. The Mixture of Agents, MOA, design involves multiple layers, each with several LLMs, operating through prompt-based interactions without the need for fine-tuning. This iterative synthesis process aims to improve response quality. The MOA approach draws inspiration from the Mixture of Experts, MO, technique, extending it to the model level. Unlike MO, which modifies internal activations, MOA operates solely through prompting, offering flexibility and scalability without computational overhead. Table 1 outlines the aggregate and synthesize prompt, which is designed to integrate responses from multiple open-source models into a single, high-quality response. The task involves critically evaluating the information provided by these models, recognizing potential biases or inaccuracies, and synthesizing a refined, accurate, and comprehensive reply. The response should be well-structured, coherent, and adhere to the highest standards of accuracy and reliability. The evaluation of the Mixture of Agents, MOA, framework demonstrates significant improvements across key benchmarks. On Alpaca-Eval 2.0, MOA achieved an 8.2% absolute improvement over the previous top model, GPT-4o, and outperformed it using only open-source models. On empty bench, despite incremental improvements, MOA secured the top position, showcasing its ability to push performance boundaries. Flask evaluation revealed MOA's excellence in robustness, correctness, and other fine-grained metrics. Additionally, MOA variants like MOA Lite offer cost-effective solutions, delivering performance comparable to GPT-4 Turbo while being more than twice as cost-effective. Internal mechanism studies show that MOA outperforms LLM-based rankers and tends to incorporate the best proposed answers, highlighting the benefits of model diversity. Table 2 presents the results of our experiments on AlpacaEval 2.0 and Empty Bench. For AlpacaEval 2.0, our MOA method, which uses 6 proposers with 3 layers, achieved a significant 7.6% absolute improvement over GPT-4o, reaching 65.1%. Our more cost-effective variant, MOA Lite, which uses 2 layers, still managed to outperform GPT-4o by 1.8%, scoring 59.3%. On empty bench, despite the high performance of current models, our approach secured the top position, demonstrating its ability to further optimize even highly optimized benchmarks. Figure 3 presents the results of the Flask evaluation using a 6-proposer mixture of agents, MOA, setup, with Qwen 1.5-110b chat as the aggregator. This setup is evaluated on Flask, which provides a detailed, skill-specific assessment of model performance. The figure highlights the MOA's performance across various metrics, showcasing its effectiveness in areas such as robustness, correctness, efficiency, factuality, common sense, insightfulness, and completeness. Notably, the MOA setup demonstrates significant improvements over single model scores and even outperforms GPT-4 Omni in several key areas. However, it also reveals a slight decrease in conciseness, indicating that the model's outputs are marginally more verbose. Table 3 illustrates the impact of varying the number of proposer models on the performance of AlpacaEval 2.0. The parameter n represents either the count of agents within an MOA layer or the total number of outputs proposed in a single proposer scenario. Across all configurations, Qwen 1.5-110b chat is employed as the aggregator, and the setup consistently utilizes 2 MOA layers. This table highlights how an increased number of proposers can influence the final evaluation scores, suggesting that more diverse inputs can lead to enhanced outcomes. Figure 5 presents a detailed analysis of the performance trade-offs in terms of cost and teraflops consumption. Part A illustrates the LC win rate against the average inference cost, highlighting models that achieve high performance at lower costs. Part B shows the LC win rate versus teraflops, using teraflops as a proxy for latency. Both plots reveal a Pareto frontier where certain models, particularly the mixture of agents approach, strike an optimal balance between cost and performance. This analysis underscores the cost-effectiveness and efficiency of the MOA approach compared to other models like GPT-4 Turbo and GPT-4o. In the realm of optimizing large language models, LLMs, recent research has made significant strides through prompt engineering techniques. Chain of thought, COT, prompting, as introduced by Wei et al., 2022, and Kojima et al., 2022, employs a linear problem-solving approach where each step builds upon the previous one. Fu et al., 2022, applied COT to multi-step reasoning tasks, while Zhang et al., 2022b, developed AutoCOT to automate this process by constructing demonstrations. Active Prompt by Diao et al., 2023, focuses on selecting the most uncertain questions for task-specific annotations. Model ensemble techniques, such as PairAnchor by Zhang et al., 2023, aim to leverage the strengths of multiple models by re-ranking outputs. FrugalGPT by Chen et al., 2023b, proposes a cascading approach to reduce computational costs. GenFuser by Jiang et al., 2023, generates improved responses by capitalizing on multiple candidates. Multi-agent collaboration studies, like those by Du et al., 2023, and Liang et al., 2023, explore interactive reasoning through multiple agents, with mechanisms ranging from symmetric to asymmetric discussions. The mixture of agents approach introduced in this paper significantly improves the output quality of multiple LLMs through iterative collaboration. Empirical evaluations on Alpaca Eval 2.0, MT-Bench, and Flask showed substantial improvements, with the LC win rate of up to 65%. This validates the hypothesis that integrating diverse perspectives from various models leads to superior performance compared to a single model. However, the method has limitations such as high time to first token, TTFT, which can be mitigated by limiting the number of MOA layers or exploring chunk-wise aggregation. The broader impact of this study includes enhancing the effectiveness of LLM-driven chat assistance and improving model interpretability, thereby aligning better with human reasoning. Thank you for watching.